So welcome back. I'm just gonna start right away where we left off. Actually, sorry, I have to. No, it's better. Cool. So yeah, yesterday we left. Actually, sorry, I have to again change the layout here. Otherwise, the recording looks weird. Okay. Cool. So yeah, yesterday we left off here where we basically, we're talking about the general principle of how we work in Houdini, where we generate something in this example, a pop sim, based on geometry that we were manipulating to have like interesting looking velocities and normals, etc., and colors. And then we did the same trick again, where we added the color to a grid. So basically, the color of the particles are copied over to the grid, and that we then basically used in a point warp that we discussed to add some displacement using a turbulent noise to the position. So this is basically, again, the output with the particle sim, and then we have the grid. And I thought maybe we could really quickly talk about using another attribute to drive the evolution of the noise, because as you can see in the very end, the noise is still like wiggling around. It's changing, and this is because if you recall the turbulent noise, the offset here is connected to the time. And if I disable this again, it's going to be static, right? So it won't wiggle around anymore. But we can also drive this by, for example, the velocity, so of the initial particles. So if we multiply the time by the velocity vector, Houdini will kind of complain, because as you can see, as we discussed yesterday, velocity is a vector, so it has this green line, and time is a float, and it has like this bluish line. So that's why this line is now like pointed, because it's saying you're basically trying to multiply a float with a vector, and I don't like that, but I kind of get what you want to do, so it will still work. So in the beginning, if I look at it again, it will wiggle around the noise, because all the particles have velocities on them, right? But then once they come to an end, the velocity vector length is basically 0. So it basically that gets multiplied with the time, so time goes down to 0, so it becomes static in the end. If we want to make Houdini happy, we could say vector to float, which basically takes in a vector, and then you can split it off in its 3 components, in its 3 floats. So now all the lines are basically blue. Blue line, I'm multiplying a float with a float, and now Houdini is happy, but it doesn't make any difference because it was working beforehand anyways. Cool. Then my favorite topic, simulations. I basically just want to briefly look at what's actually a simulation. And to see this, so I just create a single point in the origin, and I set the velocity to 10, 5, and 0. So 10 up, 10 in x, 5 up, and 0 in z. And we can display this by looking at this guy. So this is the vector, and if I change y, it basically goes down or up, as you might expect. And if I now put this into a popnet and look at it from the side, so we have basically like a coordinate system here. And if I just hit play, sorry, I just want to disable gravity for a sec. You can see it basically does nothing else than it takes the point, looks at the vector, and then it offsets in the next frame the point by that vector. So it just looks at where is it looking at, how long is my vector, and then it's just like offsetting it. Basically, as we did before when we were saying at p plus equals some vector, it would just like add that vector length to p and offset it. And if we, let this run, it basically describes just a linear function. It's basically as if you would throw a tennis ball in space. It would just like go forever until it hits a black hole, gets spaghettified, and all that kind of stuff. But there is no other force changing the vector. So basically, it just goes on forever. And the linear function, if you kind of remember this from school, it basically describes, so the function of x is described by m times x plus c. M is basically the pitch, so how high it goes. If I set my vector to, I don't know, 8 instead, then m would be higher. In this case, m in the linear function would be 0.5. Because if I look at after 1 second, you might wonder why is after 1 second 25 frames, not 24. This is because Houdini starts at 1, so we have to subtract 1. So after 24 frames, 1 second, it exactly more or less. Oh, it's 23. It should be actually, yeah. It is at 10 and 5, and that's exactly the vectors that we set here, 10 and 5. So m in this case would be 0.5. And then x. X is just the x-axis, actually. So if, again, I set this to 0, then it would still travel, but it would be always x, because the function of x is 0 times x plus c, so it's always 0, right? And the c actually is just a global offset in y. So if I set this back and I set my point position to 5 and rerun this, then it would basically, then c would be 5 in this case. Cool. Then let's maybe talk about offsetting this, because what I can also do is instead of, let's set this back to the origin. Instead of, let's kill this, delete channels. Instead of simulating this, I can also just animate it, right? By offsetting it like this. And what this does is basically, it just takes, again, the position, and it pluses the normalized vector, and then it multiplies it by this channel called mult, which is this guy. So this channel is called channel float, CHF, because it's basically a float value. And this then again is like multiplied by 0.48 in this case, because it's like with the shutter and the 24 frames, that's the correct value to offset it. And then this function only says if my py value, so my position in y, is smaller than 0, then set it to 0, which is important when I activate my fake gravity, which I'll describe in a second. But without this, if I disable this guy, it would just like go down. So it wouldn't fake collide with my ground. So yeah, this is mainly just to show that if I just offset the position by the incoming vector over and over and over again, it equals to the simulation without any vector change down the line. I can even fake the gravity by basically saying my vector, which basically looks like this, this guy. I am multiplying this, sorry, I'm subtracting this by 1 times, again, this multiplier that is relatively linked to this multiplier. So if I increase this number, it will also increase this number because it's relatively linked. So in each frame, I'm subtracting more of the velocity in y, so it gets pulled down. And this is why I called it basically fake gravity. So if I enable fake gravity, it basically does this. And if I enable gravity in the regular pop sim here, it does the same thing. So yeah, that's basically a simulation in a nutshell. It's basically just looking at what is my initial velocity and then what other forces are influencing my vector at that frame or in the next frame. And then it basically calculates with vector math the resulting vector, and then it just offsets the point based on that resulting vector. Is that kind of clear? I hope it is. Then, so this is more like a ballistic curve now because it has gravity. And gravity is a constant force looking down by minus 9.81 something something. So this is the initial velocity, and this is actually equal to, so the initial velocity, the first couple of frames look identical to our linear function. But then since it's not a continuous velocity, but just an initial velocity, it at some point, the gravity, which is a constant, it's basically a constant acceleration looking down, is overpowering the initial velocity, and that's why it's basically falling down. As a matter of fact, if we go to 1 second here and freeze this for a second, and then we enable gravity, we disable gravity here, we can see that at the same frame, it still, it reaches the same length in x, but because of the gravity, it basically just gets put down, but the vector doesn't really change. Cool. So of course, it's a bit more complicated than this, because if we now start putting in, for example, pop drag. Pop drag is basically, again, simulating air friction. And, if you put your head out on the Autobahn while driving very fast, you know that air friction can be quite hefty. And of course, there wouldn't be any air friction in space, so that's why it would continue forever. But on Earth, at some point, things always slow down. Not at that extreme, of course, but since air also has density, it slows down eventually. And this looks more like maybe an underwater bullet, if you like shoot a bullet underwater or something, because the density of water is much higher. It would also have more drag. And drag in this case is basically just basically subtracting the velocity of the current state of the vector. Then we can add, again, maybe some pop wind that we used before, and that is basically just adding holy crap, random vectors. It's basically an ambient velocity field that the vector is then influenced by, and this is basically now it's taking the initial vector again, right? Just like, cool, I'm here, but then the ambient force that we're adding, the ambient velocities of the pop wind, is so strong, and this is basically determined by that amplitude. So if I lower the amplitude here, that's 4 times less, then it's more true to the initial vector, but then at some point gets overpowered by it and gets also dragged up because my wind velocity in y is set to 2.5. So if I enable everything, so gravity, a little bit of drag, and my pop wind, then it kind of looks like this. And if we trail this, we would basically see that this is way far away from the linear function that we had in the very beginning. Cool. And again, this is a simulation because it basically looks at the current frame, next frame, and then it offsets it. But this can be also completely be faked by just a couple of vex codes that is basically calculating a fake gravity and just offsetting it by the initial vector. Is that kind of clear? I hope it became clear. Of course, I should say that this is only that simple in this example, and multiplied by the number of points. Often it's like millions of points. It gets way more complicated. Also, there is collisions that are calculated. There is in flip simulations it's a bit more complex because there is not only particles, but flip is basically a combination of volumes and particles. And so the volumes make sure that the particles don't go everywhere, but they, happen relatively close together in that volume field they live in. And so there is a lot of vector math happening before the solver knows each vector for each point, and then basically it offsets these points. Cool. Then maybe let's talk about solvers. Again, I'm using grids because I don't know, like grids. We have two grids. We have one grid. We make it black. Then we have a sphere. We make the sphere red. And then we do the same thing as before. We transfer the attribute from the sphere to the grid. And the sphere has an animation on it. This is based on just a sinus function, which basically rotates it in x or transforms it in x and z. And since it's a sinus function, it's wiggling around like this. What we can do now is what we did before. We take the position in y and add the x value of color, or the red value of color, CDR, which means that everything that is black stays the same. Everything where it's red, it basically gets lifted. It gets displaced outwards. So we have this weird little thing. And the exact same thing can be done in VOPs. So again, as we said yesterday, VEX and VOPs are basically the same thing, but VEX is multi-threaded, VOPs isn't multi-threaded, and this is basically just a visual representation of the code that we otherwise can write. So this does exactly the same thing. It takes the position and it adds to the position the vector red, the red channel of the color, and adds it to the position like so. That's why this and this is exactly the same. However, if it gets more complex, then Vex will always be a tad faster because this is multi-threaded and this is not. Cool. So now we're doing the same thing, but we put it into a solver. And if we look at the result, we can see it has this trail effect. And since the color is, fading out over time, so is the displacement in Y. And basically, what is a solver? If we dive right in, we can see it looks a bit more complex than it actually is. We have the previous frame, which is basically our original grid, right, the black grid. And then we have input 2, which is our sphere that's moving around. So if you look at this again, I connected the grid into the first input, and I connected the sphere into the second input of this node. And so this is input 2, so this is the sphere. And this is actually input 1. That's the grid. And that's the grid on the current frame. And that's the grid on the previous frame. And that's a bit of, weird if you see it for the first time. But basically what we're doing is we're doing the exact same as we did outside. We're transferring the color from the red sphere onto the grid from the previous frame, right? So it basically, does it with one frame offset. And then we can do basically the same trick. I should say that if you're inside of the solver, you see, if you look here, I'm on object level and then this workflow basics and principles level. And if I dive inside, I now dove inside 3 levels actually. I'm in this S thingy and these in the D context and then the solver trail. So if I go up, you can see there is a bit more happening than what I dive in directly to, because I'm basically going 3 levels down at once. And if I go up, I can already see that because I'm adding, because this is a solver and it basically records what happened before, and then it continues to do the same action again and again, it basically, trails that red color transfer to the grid. And what we then can do to make it fade out is we can just multiply the color by 0.9. So what will this do? It will basically, on each time step, which in this case it's frames, it will multiply the color by 0.9. So it will lose with each time step 10% of its value. And if we now go outside, this happens on every frame. So this is why my initial color is still 1, but then after one time step, it's 0.9, and then it's 0.8, and then it's 0.6, and then it's 0.5, and it goes down. Although technically it's 0.9 times 0.9 times 0.9, so it's a bit of a different curve. But this is basically this is how a solver works. It just records stuff and does stuff over and over again on each time step. And again, I can do this in Vex by just multiplying the color by 0.9. Or what I can also do is I can, this is a bit more complex, but I can get the color of the attribute before and then mix it with the current color, and then set the bias to something like 0.05, which result in the exact same thing. So it will also fade over time. So again, this and this is the same, but this is a bit faster because it's Vex. And then, the output of this is actually, just that. And then we do the same trick as before. We push everything up based on the CDR value, either in Vex or in VOPs. Again, it's exactly the same as here. And that's it. hope this kind of makes sense. Cool. And then, oh yeah, there is another important aspect, which is point count changes in Houdini, and to keep the data basically consistent. And a good example of this is, of course, we start with a grid again, make it again black, and the colored sphere. And the colored sphere in this case does a bit of a different move, but it's also sinus functions. So we do the same trick again. We run the solver multiple times, so it records basically the attribute transfer. However, this is actually a good time to maybe speak about substeps, because as you can see, the sphere is quite fast. And the sphere in this case is a bit too fast for the solver, because each time step is quite the distance it travels each time step is quite big. So we get stepping. And stepping is one of the common issues that we always face with when we kick back stuff to animation and say, this spaceship is traveling at like 15 million hours per second. It's impossible to sim. This is basically the reason. What we can do is we can, of course, increase the substeps. So make this 3 instead. And then, it basically, like we discussed yesterday, if I switch the frames from integer frames to float frames to 0.1, then it does it on 3. So it changes here, and then 1, 2, 3, nothing happens. And then it goes again, and then 1, 2, 3, and then 1, 2, 3, and then 1, 2, 3, and then 1, 2, 3. If you look here, it basically now every third of a frame, it samples the new color. If I set this to 10, then it does it on each point, on each tenth of a second, basically. But of course, on the cost of time, right? So simulation times will be 10 times slower as well. In this case, it doesn't really matter. I can set this probably to 100 because now it does 100 subframes. But now you can see, okay, it does 100 subframes, but now it's relatively slow in comparison to what we had before, which was quite fast. But I think 3 is okay for this. So what we can do now is basically, again, we do the same. We scatter some points based on the density attribute CD. So it just scatters point where there's density. In this case, where there is color. And then basically what I'm doing here is just like randomizing a bunch of attributes. Orient, we briefly discussed this yesterday. That's the banana on a stick thing that I said, the 4-dimensional vector. And I'm also randomizing p-scale. And then I'm saying I'm creating an attribute, which is an integer, and that's called ID. And that equals to my point number. So if you recall, my point numbers are just these guys. It's just, the number of points. We can also display this like so. Each point has a number, right? And this, unfortunately, of course, is changing because I'm creating on the fly new points. So as you can see, my point number is not consistent. It changes per frame on every point. And so will my ID, because my ID is basically now my point number. So also my ID will just, change every frame. However, why is this important? If I blast anything away that's, not red, but black, and then clean my color, so I don't see the color, but I still have, my ID attribute here and my point numbers. If I now take this beautiful pig head, and Houdini people are weird, that's why we are copying pig heads, to each point, then you can see that it flickers, right? And the reason it flickers is because my ID is changing on every point per frame. So there is no consistency in how this is copied, because Houdini just doesn't know where each point lives, because it's jumping all the time. So also my randomization of the p-scale and the orient is also jumping, because it's also basically based on the ID and the changing point count. So that is pretty important, and there is a number of ways you can solve this. One of them is basically to pre-populate the whole thing with points, and then create. So I'm just scattering points on the grid, on the black grid, and then I'm randomizing orient and p-scale, and then I'm also creating the ID. And this, of course, is static, right? There is nothing happening here. So this will stay static as well. And now I'm attribute transferring the color of that sphere to these static points, right? And then I'm blasting away everything that is not red, basically. So now, if I look at my point count, you might say, well, the point count still changes per frame, right? And yes, that is true. However, if we look at the ID attribute that we created right before we blasted everything away, because this blast is basically the culprit that makes our point counts change over time, right? Because it's basically dynamically removing everything that is not red. And since I'm adding more points, I'm adding more color that I then get pruned, it's still, the point count is still changing. However, if I look at my ID attribute, which I have to probably, it's already set up. And this is constant. And why is my ID attribute constant? Because I created it here, right? I created the ID attribute here while I still had a constant point number that wasn't changing. And by basically storing this, so I'm basically saying I'm creating this extra attribute that is based on my point number, but I'm storing it, and then I change my point number, I still have consistent IDs, right? Because the IDs aren't touched. It's only the point count that is touched. And this way, I can use this unique ID per point that's not changing over time to copy the beautiful pigheads. And yeah, this is pretty important also for, imagine the particle simulation from before, for example. So this guy. A particle simulation like this always comes with IDs as well. So if we look at the geometry spreadsheet here and we look at ID, you can see that each particle has a unique ID. See, and it's not changing over time. This little particle here is ID 208, and it won't change that ID no matter what happens. And the point count, of course, is changing over time because I'm injecting more points into the simulation at each time step, right? It's getting more and more points. But this concept is very important because, if we get nodes on, I don't know, we like this weird simulation, but I don't like this strand. Can you please remove this strand? Then I can say, yes, we can remove the strand because I know it has the ID 208. So basically what I can do is I can just go to the points and then attributes and then ID. If I find it. Oh, it's probably at the bottom somewhere. Yes. And then I can say, cool. So I remove this point based on its ID, right? But it's important that I'm like filtering by ID and delete it. So now this point is gone, and this strand is also gone because this strand was generated by that ID, of course. So now it's back. If I wouldn't do this, if this blast wouldn't say at ID equals 208, but I would just like blast the point itself without being in this ID mode. If I would just like blast it like this, and it would say, cool, I'm blasting point 208, then it would eventually come back at some point because my point count is changing, right? So I'm not supposed to blast or prune stuff, delete stuff based on the point number, because the point number is changing per frame, but on a unique ID. And that unique ID is just a very important concept. Cool. I hope that made sense. Cool. Looking at the time, we have about an hour left. So we can take a look at for loops and for each loops. So I would basically try to complete this basic section, and then we can go over and look at, probably the next time then, look at this fluidity guy. And this is like, this will take the most time because in this setup, we will set up everything. But then, you know, all the consecutive following setups will be a lot faster because, as I said yesterday, since it's procedural, I'm only changing the source, the solver, and the shader in the end, but everything else stays the same. Good. So let's talk about for loops and for each loops. I am starting again with a grid, of course. And I am noising this up by just, you know, this is basically an attribute noise based on P. We did this before. And now I basically just delete everything, but keep the points. So I have this point cloud. And then I have a box, and I'm copy to points like the pickets before. These boxes to the points, right? And currently they're not doing anything. They're just, this box gets basically instanced on these points. Now I have this connectivity sub, and that connectivity sub basically checks of my input geometry, which pieces are connected. So it basically looks at, you know, I can also show this by saying here 3D connectivity, and go to primitives maybe. Yeah. Yeah. So basically it creates an attribute per connected piece. And in this case, this is called class. So if I visualize class by just going to this thing and clicking this class attribute, and then going to my visualizers, I can see that this class attribute is basically unique per geometry. And I can also look at it in not the points, because this lives on primitive level, right? The connectivity type is primitive. So I have to go to primitive. And here I can see I have this unique attribute per box, and it ranges from 0 to 175. Why does it range from 0 to 175? Because I have here, my point cloud has 176 points. So since we're counting from 0, I have 175 plus 0, so 176. Cool. So what I could do now is I can transform, put down a transform, and use again the $t, which is time, multiply that by 100, and then I can rotate the whole thing. Pretty boring. What I also can do is I can drop down a for each loop. And the for each loop is basically just a context in its own, where it's basically looking at just one of them. And the important thing is that we have this connectivity thing, because my for each is looking at a piece attribute, and at this time it's class. If there's typo and it's like class 2 or something, then this wouldn't necessarily work, because I need a consistent attribute here that we created with the connectivity. So now, basically everything that I do in here, in this context, in this orange box, it's running only on not the whole geometry, but on each object. So what I can do is, for example, I can rotate it as well. So same function, $t times 100, but I'm setting the pivot to the center of that object. And since this is running over all the cubes over and over again, at the end of it, they basically all rotate around their own pivot. So that's the difference between this one, where it's a whole geometry, and this one, where it's basically just, rotating around their own little pivots, because my pivot is set unique for each cube down there. Cool. So that's the first gotcha for each loops. It's basically just whatever you do inside of here, it happens not on the whole thing, but like on each connected piece. Now, to take this a bit further, what you can also do is this, where it's a bit abstract, but now each of them has a different rotation speed. And why is that? Well, it's the exact same setup, right? We have the connectivity spheres here, we have a transform here, and that transform scales it down a tiny bit each cube. And then the only thing that I added is the rotation is still, some value times $t times 5. So that's the reason why it's rotating. But then there is another value that the time is multiplied to, and that's this one. And this one is basically a detail attribute. So it's basically the detail of ... meter. So these ... means basically go outside of this node, right? Go outside of my transform. So now I'm looking here and look for the node called meta. So it's basically this guy. And on that meta node, there is an attribute, a detail attribute. This is why it says detail here. That's called iteration. So if I go to this meta node here and I go to the details, I can see this value here. It's the iteration. And it's currently set to 175. So this is basically a unique attribute per primitive. That's why it's living on the detail attribute, because as we learned, points, point attributes live on each point. Primitive attribute lives on each primitive or face, but detail is only one attribute per whole geometry. And in this case, that whole geometry is that box. And it runs over that for each. So that means, what does it all mean? If we look at the point position, the point number, we have, and we look at this maybe like so. This is 0.0, and this is where's 0.1? Ah, here. Here's 0.1. It's a bit higher up. This 0.1, this 0.2, 0.3, 0.4, etc. And if we now look at the rotation speed, we can see that 0.0 is not moving at all. And why is that? Because for 0.0, this iteration attribute is 0. So if the iteration attribute of this guy is 0, then 0 is multiplied by 5, which is still 0, is multiplied by the time, which is still 0, because anything times 0 is always 0. So my rotation of this cube, of cube 0, is 16.9 plus 0. So it's 16.9. However, on point 1, it is 16.9 plus 1 times 5 times $t. So there is a slight rotation on the first cube, right? It's very, very slow. And then on 2, the value is 2, so it's 2 times 5 times $t, and so on and so forth. And that's why point 175 is basically, we look again at it, 16.9 times 175 times 5 times $t. So this guy is going crazy because his rotational speed is very, very high. So basically, the whole idea of this for each together with the iteration of this meta import node is basically to have a unique attribute per point that is then, or per piece that then can be basically modified. Hope this makes sense. If not, please shoot any questions that might come up. Cool. So what can we do with this? For example, if we look at this guy, it's all a bit abstract from now on, but this is basically this weird head that has all these floaty particles, and in the end they converge together to the head. So how is this done? We start with just the head, the test geometry. We remesh the head to have less polygons. We transform it up so it's a bit bigger. And now we do basically the same thing. We put it into a for each loop. And we have the meta import node, and we have the transform. And the transform is now has 2 values. So it has the iteration value, like before. That's basically referenced from that meta 2 node. And then it's multiplied by this. And this is basically a channel called, if I go outside, because that's the first ... go outside again, look for the node called null1. That's this guy. And then look on that null1 for rotation amplitude 2. So if I look at this guy and I look at rotation y, it says basically down here at parameter, it says rot amp 2. So it takes the num iteration value of the meta import node and multiplies it basically with this value. And this value is something that I animated. So it's just 2 simple keyframes ranging from 1 to 79. And they basically animated from 3, 2, and 3 in X, Y, and Z. So the result of this is basically that for each primitive, so for each polygon, as you might say, or face, it takes that value and then multiplies it by the num iteration value, which is again ranging from, I don't know how many pieces we have, ranging from 0 to 167, because we have 168 pieces. And hence that's the result, where each of them has a different speed rotation. And if we, for example, look at a point number, not a point number, a primitive number, with a low value, for example, 0, this guy shouldn't move at all, right? Because its num iteration value, this guy from the meta import node is 0. So 0 times these rotation vectors is still 0, right? So if we look at it, it for sure doesn't move at all. Like 0 stays at the same time. But if we find like a speedy one, it probably has a high primitive number. This 159 is pretty high. So its rotational speed is also pretty high. Basically like the cubes that we just saw rotating. Cool. So this is basically for each loops in a nutshell. So if you have a lot of geometries and you basically want to do something to all of them, but in a slightly different way than for loops. For each loops is the way to go. However, there is also another concept, and that's called for loops. And for loops is basically very similar, but different in a way that it's not running over every geometry, but it basically does something, and then it does it again, and then it does it again, it does it again, kind of like a solver, but a bit different. So to explain this, if we have a sphere, right, and we transform, something changed, and we transform the sphere by 1 in x, then it gets transferred 1 meter in x position. Good. If we do the same, so that transform in x1, but in a for loop, right? We have at the end of the for loop, we have this iteration number. And this currently set to 0. So 0 times, it didn't even start, right? If we set this to 1, then this operation is done exactly 1 time. So I'm setting it to 1 meter to the right. If I set this to 2, then it's 2 meters, 3 meters, 4 meters, 5 meters, blah, blah, blah. It's basically what you might expect. If I set this to, $f, then we're kind of like, maybe $f minus 1. We're kind of like in that realm where we have been with our linear function, where over the course of this, it's going to, linearly go upwards. Not because it's a simulation and it's basically looking at the vector and then it's offsetting it by the vector, but just because I'm setting the x and the y on each iteration, not each time step, just up 1 level. So whatever I do inside of here, I can just say how often I do it, basically, with this iteration number here. So same goes for, I can add another one for scale, and just similar to the trail and the solver sub that we just saw that it's fading off, I can set the uniform scale to 0.8. So with each iteration, it gets a tiny bit smaller, right? Until it's almost 0. And I can combine this and say, in every time step, transform it in x and y, and then also scale it down. So in this way, with each time step, it gets smaller and gets transformed. I think you got it. So we can use this concept to do interesting stuff. For example, if I create an attribute called active, this guy. So I'm dropping down an attribute randomize and saying I want to create a primitive attribute that is called active. And it just creates 2 values, 0 and 1. So if I go here, I can see it created a float attribute because it has like decimals. And they basically range from 0 to 1. If I want to look at this, I can, again, just click this active attribute. And here I can say, here you can see that on this visualizer, everything that is 0 is purple, and everything that is red is 1. So 0 to 1. And since there is no in-betweens, since it's just like these 2 values, there's no gradients whatsoever. It's just like, this is 1, this is 0. It's basically as if we would say in a wrangle, if random primnum is smaller than 0.2, then make the active attribute 1, otherwise 0. So this probability thingy is basically just a bias. So now everything is 1, now everything is 0, and the chance is basically 0.2. And this is changing, though, based on the global seed. So if I change the seed, I change, of course, the outcome of this node. And then I do the same on an attribute that I call z-scale. And z-scale, again, it doesn't have two values. But this one I allow to have like different values. So basically not only 0 and 1, but like 0 to 1, basically a normalized attribute. You can also look at this guy, just like clicking this. So now I'm looking at Zscale, and as you see, there is a bunch of decimal in-betweens values in here. So if I now put down a poly extrude, the poly extrude has some options. So for example, that's the distance of what I want to extrude, and there's like inserts and whatever, what have you. But I'm only running this on a certain group, and that certain group is wherever my active attribute is 1. So I'm only running this on, again, on the red ones, right? Only the red ones get extruded because I'm saying I only want to do this. I can also do it the opposite and set this to 0. So I would only extrude everything where the active attribute is 0. Now, the Zscale attribute, as we saw before, has random values all over the place, right? And I can use this as the distance scale. So you might wonder, well, the distance scale is this guy, right? Yes. But there's also, so this is the main display distance scale, but this is basically a multiplier. So if this is set to 0, then everything is set to 0 because 0 times something is still 0. But if I set this to 1, then the distance that this is extruded is equaling my values that I see here on the Z-scale. Cool. So if we now take this little setup, which is quite basic, and run it over and over and over and over again, then we would get something like, again, I set the iterations. Actually, I can delete this and set it to the left. If we do this over and over and over, then, sorry. Yeah, we get something like this, where we get like a random abstract growing thingy. Not sure in what manner you would use this in production, but the concept is interesting because this attribute randomizing and of these two values is happening on each iteration. And since on each iteration, the geometry itself changes, right? So do the attributes. So on the second time step, if you go to frame 2, it now basically creates an attribute called random, called active and Z-scale. But this time it's maybe picking this guy and this guy because it's completely random, because I also the global seed again uses this iteration attribute. Iteration attribute. Plus some value that is completely arbitrary. So it on each iteration, on each time step in that frame, in that case, because I'm setting this to $f, it changes randomly. So it creates this random structure because the attributes are distributed randomly across the new created geometry. I hope that makes sense. Yeah. So again, to recap, for each loops, it's basically just running the same thing on each connected primitive or connected point or connected whatever have you. And for loops is basically doing the same thing over and over again, but different based on the outcome of the previous iteration. Cool. And now, well, we can do like a little poll maybe. I can either talk about creating procedural buildings that are quite ugly, I have to say. Or we can start with the first setup, which is the fluid dancing guy. This is called substraining because I think the the thing that is easiest to learn Houdini with, and is also like the fundamentals, is actually to get to know the subs, so all the operators that you can see here, because they kind of make the most sense to anyone who knows other DCCs, because they're basically just operations. And then, dynamics, context, and all that kind of stuff that's a bit more abstract in a way, comes after. So that's why, this building is completely done in subs. I think there's no vex whatsoever in here. And then we can, use this to produce a bunch of different buildings procedurally, and then this can take in even further, and then, with the copy to points, like the pickets that we had before, we can basically create layouts of cities, for example, and then we can create cities, which is, again, this example, which is like these abstract city things. So I don't know. I don't care. We can do we can go through this HDA, which basically procedural buildings.
Yeah, I agree, because everything else is like effect specific. So this is like for non-experienced Houdini artists who likely work in different departments, who use assets and, I don't know, use the workflows, HDAs and whatsoever. I would suggest we continue with the sub.
Great. I think, yeah, that's
as long we go back to fluids at some point, because I would be really, really interested in it.
Yeah, I mean, probably not today, because we
of course not.
Have half an hour left before.
Of course not.
Before we have to, end this because of Julius. Cool. So then I would start with the building. So again, this is kind of like this is not really an HDA because it's not an asset yet, but it is a subnet. So basically, if you create a bunch of nodes and you do something and you have your setup, you can click this little subnet button here and wrap it up. Basically, like in Nuke group, where you then can dive inside. And the cool thing, though, is that once you did this, you can build a procedural. Actually, there should be an output node here. Build a procedural building in this case, and then reference some of the parameters that we can see here on top level. So when I change, for example, the building height here, right, which is basically defining the height of the building, and I dive inside and I look at this poly extrude, I see that the Y component of this translate poly extrude, that is basically just extruding something in world position upwards, is set to 13.15, because this is basically the channel that we just looked at outside. So again, it's a channel that go outside of yourself and look at translate Y. So if I go here and I look at the building height, it's called translate Y on the parameter right there. I can't go over the mouse with it because it just disappears, but you can see the parameter is called actually translate Y. So when I change this guy outside here, what actually is happening is that this translation of the poly extrude, so the distance that I'm extruding, is actually what's changing inside of here in the setup. And the way you do this is basically on every node, there is this little gear wheel thingy, and you can change the parameter interface here. And this looks a bit overwhelming at first, but basically you can ignore all this and just look at this guy. because this is the parameters that you can create, and you can like create buttons and colors and whatever, but we don't need that for now. This is the existing parameters on this little thing. So for example, if I want to add another parameter, what I can do is I can go inside here and say, yeah, I want the depth of my subdivision, for example, as well in here. So if I dive inside and press apply, then I have this new parameter called depth, and I can change the name here, depth of the subdivision, for example. Apply. So now it's called depth of the subdivision, which is not very helpful. But if I change this now, it will change my mesh accordingly, because inside it's changing that parameter on the subdivision level. So this is basically how you can, and then if I want to, I don't know, if there is another thing that I find useful, for example, the scale of my UVs, I can also like drop them in here, hit apply, and now I have the scale. So if I look at my UVs, and if I change this now, I can procedurally, change the size of my UVs, like so. And the cool thing about this is if you have your little tool built, then you can make an asset out of this by just going here and say new digital assets from selection. And this will basically create, don't know why it's not working right now. Because I think it's an unlocked asset already. But you can basically, if there wouldn't be a lock here, you can just like press new digital asset from selection, and this will create basically a single file called building3 HDA, and that you can then open up if you have the plugin installed, the Houdini engine plugin, in any other DCC like Maya, Unreal, whatever, and then you would basically have the same controls that you have here directly in Unreal, and can change the UVs and create a bunch of different buildings on the fly. But let's see how we built this building in the first place. So it all starts with kind of like the blueprint. So in this case, I made a little switch because it's either, actually, let me show this. So it's either based on this blueprint, which is based on a circle, or it's based on another one that is based on the grid. So I hit the switch here, my blueprint changes to this grid, which is much smaller in size. That's why my building just got very thin. But just so that you could basically also promote that switch to here, and then basically say, I want to have a building based on a circle or a grid or whatever. But let's go back in. So right now it actually looks at the circle. So we start with a circle. And I'm reversing the U, doesn't really matter. And then I'm point jittering the points. So basically, if I look at the points, I'm just jittering up the position. So if the set is 0, then it's not jittering at all. If I increase this scale, then it gets jittered in X and Z, but not so much in Y, because in Y it wouldn't matter. It wouldn't be that helpful, because if I would do this, my resulting building would probably look pretty weird, because it's not flat anymore. So I get like this weird distorted normals, as you can see here. So I definitely also want to have like a 2D blueprint plane, basically. And then this point jitter, actually, this seed is referenced on the top. So if we go again outside, so if I look at the seed, where's the seed? Shape seed. If I change this, it will basically generate a new building, because everything that is following down here is based on this point jitter. Because if these points, create a different shape, then my resulting building is always different, right? So this shape is actually this shape. Cool. Then the transform here is basically my building, how broad the building is and how long the building is. So that's basically the building width and depth. So if I increase this, I get a very long building. And if I make this bigger, then I get a very broad building. And it's just based on this transform, because I'm basically changing the blueprint. Right. So 3. Cool. So now I have the blueprint, and everything, builds on that blueprint. So there's different sections to this. There's the pillars, there is the wall and the buildings, there's the ceiling, and there's the fence. Kind of like in Nuke, if you do like something to, I don't know, that part of the element and then another part of the element and then the other part, it's the same backdrop mentality. So let's start with the pillars. So I am basically taking the points of my blueprint, so these guys, and then I'm copying boxes onto them. So basically, as with the pickets before, we're just instancing. Almost, it's not instance because I'm not packing and instancing them. I'm just copying that geometry onto the points. And then I'm Booleaning it out with the building. So basically, I'm taking the blueprint here, and then taking this geometry, and then the bool. I think it is set to, the intersection of that is basically giving me just the intersection between my copied boxes and my blueprint, which is basically this geometry here. So this now I can take and do like a connectivity. We've seen that before, right? When we did like the class attributes and the for each. And actually here I'm doing a for each. And in that for each loop, I'm doing the same trick as before, setting the pivot of each to its centroid. So if I look at this guy, it's, the centroid is basically inside of them. And this now I can use to first poly extrude it by the same value, than the poly extrude. So the other poly extrude 1, because this guy is called poly extrude 6, right? Not very descriptive. And I'm looking at poly extrude 1 translate Y. So this is a relative reference to, I can actually display this, show for selected nodes, to this poly extrude. And this poly extrude, again, has a reference, if you recall, to my building height at the very top. So this 22.59 is referenced in here. And this, again, is referenced in here. So if I change the top level thing, this node, this poly extrude, together with this node, will have all the same values. And that's, again, one of the core principles that are very important inside of Houdini, that you build procedural setups with this in mind, that you set everything relative to each other as much as possible so that nothing breaks down the line. Because if I wouldn't have set this to the same value, but hard-coded it to 5, then my building would look very differently, because my pillars would be very small, because they wouldn't dynamically update to the height of the building. So let me revert this. Good. So, and well, this, yeah, basically that's it. Now I'm basically arraying this to my poly extruded building. So I have to foreshadow here a little bit. I'm using again the blueprint, and I'm poly extruding this in height, and this I'm using as a array, as basically you can almost say that it takes this geometry and then it projects it onto the second geometry input. So it projects these pillars onto this my extruded geometry, so they're flush together. And then I'm giving it normals, and then I, giving it UVs, so I can look at them like so with a UV unwrap, and then I can make them, smaller, bigger, whatever. And this basically completes the first section. That's the pillars. So then the wall and the buildings. We've talked about this again already quite a lot now. I'm poly extruding the blueprint. I'm deleting the top. So why do I have this top group? Well, the blast node is referencing a group called top, but where does it know where's the top of this thing? Well, if we go to the poly extrude, there is the front group and the back group. If you extrude something and you don't output the front or the back, then it's basically just a tube. But if you output the front and the back, you get the caps at the bottom and the top on an extrusion. And you can group them and give them a name that is descriptive, in this case, top and bottom. So I'm blasting the top based on the group that it was created on the poly extrude. Then I'm subdividing everything by, I think it was 2 actually. And now I'm booleaning this out with something, right, that creates these fake windows. And what is the something? Well, this is the second input. And the second input, I'm using also the blueprint as a base. I'm converting this into a line with points. So there's a couple of points here. I'm splitting the points so they're not connected anymore. And now I can use a primitive SOP to scale down each of the newly created primitives. Because if I wouldn't have split up the points, then the primitive would scale down the whole thing because it's connected. So I have to make sure it's not connected anymore. So I can split them off individually. This is actually a good example. I could have done this theoretically in a for each connected piece loop, right? Where I say, split all the points and then scale, set down a transform, and the transform is set to 0.9 or something, would have given me the same result, but this is computational much quicker to do it basically with a SOP rather than doing it on each of them individually. Cool. Then I'm resampling them. Resample basically just means I can resample the curve, so I can define the resolution that this curve is made up of. So now it only consists of 3 points, and now it consists of like a lot of points. So if I would throw down a mountain, now it would look, pretty high res because I have a lot of points, like so. But if it's pretty low res, then the mountain wouldn't look as nice. And this resample is not just some value, but this resample is, as you can see, referenced again to the translate y times 0.7. So it also looks at, well, the translate y is this guy, right? It looks at how many units was my initial building extruded by, and then it basically creates as many points times 0.7, which is like an arbitrary number that just looks good in the end. And this defines the number of windows that are created. So you'll see that in a second. So again, the poly extrude again references the same translate y as the main poly extrude, which is basically the building height and the top level parameter. And then I'm using a translate to scale it down a tiny bit, because now I actually have a lot of points, right, that are sitting right on each side of the building. And they're a tiny bit smaller, so they're insetted, basically. This is why I added like this transform. Because now I can use these points to instance, again, just boxes on it. Tiny little boxes. So I end up with this. And this I then can, translate again. I think I translated it a tiny bit in. And use this as a Boolean. So I create basically windows. So I just take this, bool it out with the newly created points. And again, since this resample and this poly extrude are relative referenced to the height of this thing, it adapts to whatever parameter I'm setting here. So everything is connected, if you might say that. Cool. So then I giving it normals again. I UV unwrap it, so we have UVs that are okay-ish, and merge that together with the pillars that we created before. So that wraps it up with the walls, basically. 6 minutes to go. Sealing. So sealing is basically using this poly extrusion of the building, where we basically blasted the top, right? But now I'm blasting everything but the top. So basically saying delete top, but delete non-selected. So I isolate the top instead of deleting it. Now I'm poly extruding that. This time it's not referenced to anything, because this is basically not dependent on the building height, for example. This is always the same inset, basically, that I'm creating here. And then I'm poly extruding that inset to get this tiny inset here. And then I'm giving it a normal, again, doing UVs, putting this together with the rest of it. So I get this building with always the same little thing, little bump. And then last but not least, the fence on top of the building, right? So how do we create the fence? Well, we can use this as a reference, because it already comes with the points, right? So what we can do is we can poly extrude this and do a little inset. So it's going in a little bit. Then we transform it a little out again. We convert this into a line. We resample this again as we did before. This basically specifies the number of fence pillars, so to say. And then we use just a little tube, and we copy this to the points. So this gives us a lot of tubes around the top here, right? At the same time, I'm again, I think, I don't know. Oh yeah, I'm using the height of the tube. So my tube has a certain height. It's 28 centimeters high. So yeah, as you can see, this building is not really real scale. But I'm referencing basically that height of each tube in this transform, and I'm using this as a translate. So basically, I end up moving this line from here to here, right? Because I'm just offsetting it by the height of each tube. Then I'm splitting the points again and polywire it. Polywire basically just creates geometry out of a curve based on a wire radius. So if I make the wire radius really thick, I get a really thick curve, really thick geometry. And then I merge that in. So now I have the pillars, and the pillars have at the top this railing, and it's super low poly because, as you might recall here, I don't want to spend a ton of geometry on this, because on my procedural 3D at the very end, you can't really see them. They're very low poly to keep things nice and efficient. Cool. So I give it normals, I UV unwrap it, and merge it together with the rest of the shebang, and end up with my procedural generated building. Important to say is that subnets do display by default whatever the display flag is set to. So if I set my display flag to this poly extrude and dive outside, I can change my building height, and basically nothing is happening because I'm actually viewing this guy. So you either have to make sure that your display flag is always set to the very end of your setup, or you just create an output node which will force this to be the output, no matter what I selected. So you can look at the poly extrude here, and if I dive outside, it still will look at the output node. So, and then basically what I did is, as we saw before, every parameter that I felt handy to have on the top level, I just promoted to the parameters here, and you can make this even more complicated with like much more different things, like, I don't know, railing size and height, and add a lot more stuff to this, like little window sheets or what have you. But this is just a very, very basic example of how you can create an HDA. And for example, that famous city sample that you can download from Unreal, which was heavily featured in the Matrix movie as well. That was basically built with a lot of these HDAs, because they didn't hand model all these things, of course, but it was like procedural generated based on real life data and Houdini. And that wraps it up for today. The great thing is that we only have to talk about how we can put this thing again in a for each loop and run this to, thank you, run different variations of the same thing that then can be scattered in Solaris and instanced very efficiently and rendered in real time almost. And then we can talk about the fluid guy and all the other setups, because now we basically are finished with the basics. If there are any questions, please shoot now or hold the breath forever. I'm going to stop the recording.